Are you ready for functions? Some more functions. Today we're going to look at a few questions from past papers as a follow-up to part 1 of the same topic. But before we do that, there's a few extra concepts that I would like to discuss with you. Now we know that when we deal with functions, we sometimes encounter problems on transformations. It is important for you to know and understand and be able to identify the different types of transformations that can occur on functions. First of all, remember our function as f of x. If we consider it as f of x, there are a few things that can happen to f of x. For instance, we could have f of negative x. Now this is slightly different because we've introduced the negative. And if you notice, the negative is multiplying x. It means that all the x values in our function are going to be multiplied by a negative. This is equivalent to reflecting on the y-axis. This represents a reflection on the y-axis. That's number one. Number two, you could have negative f of x. This time around we're multiplying f. Please remember that f is the same as y. What it means is that we're multiplying all the y values of our function by a negative. Now this is equivalent to reflecting on the x-axis. Reflecting on the x-axis. Thirdly, we could have the scenario f of x plus a. Now this is equivalent to shifting. It's a translation. We're shifting our graph. Now this may sound contradictory, but if you have plus a, we are shifting to the left. Keep that in mind. When you're adding, you're shifting to the left. And likewise, when you're subtracting, you're shifting to the right. So negative a implies we're shifting our graph to the right by a units. This applies to trig functions as well, by a units. We could combine two of these transformations. Take, for instance, this scenario where we have f of a minus x. A very interesting scenario. There are two transformations here, as you can probably see. The first transformation is the negative. Now, this is the same as the negative we spoke about there in 1. So what we're doing, we reflect. Since it's negative x, we're reflecting on the y-axis. And then the second transformation that we have now is the a. Probably you can see that this is positive a. So basically adding a, which is equivalent to number 3 here. So step 1, reflect on the y-axis. And then step 2, we shift Since our A is positive, we're shifting A units to the left. Remember, when it affects X, it always does the opposite of what it seems. Now, there's one more scenario I would like to present here. Let me call it number 6. If you have f of x plus a, remember we said f is y. So we are adding a units to y. This is equivalent to shifting our graph a units upwards. Similarly, if it's a minus, a would imply we're shifting a units downwards. If we had time, I could give you some illustrations of this, but I'm sure you can check your textbooks. They might have a few examples of this. Now, it's important that you familiarize yourself with all these possible transformations that you can get. You may encounter them in problems. Now, having said this, one other aspect which I would like us to talk about is a domain and range. Now remember, domain refers to x values. And then range is y values. However, these are not just x and y values. These are values where the function is defined or where the function exists. And we basically have 4 functions. Now let's look at a parabola. For a parabola, generally we say that our domain is x element of R, meaning our parabola exists for all values of x, generally. Now, if you analyze a parabola, whether the value of a is positive or the value of a is negative. Remember, here we said a is greater than 0 and a is less than 0. Now, you can see that your parabola exists for all possible values of x that you can think of. So for x, real number, your parabola will always exist. If I were to draw a vertical line at any point there, vertical line from the x-axis will always coincide with the parabola at one point or the other. Now remember, these arrows were saying etc. So from any point on the x-axis, you can draw a vertical line that will touch your parabola. Hence we say all real numbers. That is our range. Sorry, our domain. What about the range? The range of a parabola is dependent on the turning point. Now I can tell you that whenever a is greater than 0, your range is going to be y greater than the y value of the turning point. You have to calculate the y value of the turning point. And then y will be covering all real numbers that are greater than the y value of the turning point. However, for a less than 0, your range will be y less than or equal to the y value of the turning point. And y will be all real numbers. The next type of function would be our, let's take a hyperbola. Now you remember that a hyperbola has got two asymptotes. And it's important to remember that on your asymptotes, the graph does not exist. And this horizontal asymptote we said is y is equal to q. And this one is x is equal to p. Your domain is given by x, element of R, all real numbers, but x must not be equal to p. The range y is all real numbers except q. Thirdly, we look at the exponential function. Please refer to part 1 of this video for details on these types of functions. If you remember your exponential function, this is one example of an exponential function. Sometimes it will appear as this, as an increasing function. Now this horizontal line is our asymptote. Which is given by the equation y is equal to q. Now as you can see, if you draw a vertical line from the x-axis, you will always encounter the function. From anywhere on the x-axis, you will encounter the function. Now remember, the function continues in that direction. So we can say that our domain is x element of R. Means x is all real numbers, no exceptions. And then our range, now if we had, let me just superimpose a y-axis here for argument's sake. Now if I were to draw a horizontal line on the y-axis at this point, you can see that we'll never encounter our graph. Any point along these lines that I'm drawing. However, as soon as I pass the asymptote, I'm going to encounter our graph. Every time I draw a horizontal line, I'm going to encounter my graph. So every time I encounter my graph, it means the graph exists for those values of y. However, when I do not encounter my graph, it means it does not exist. It's not defined at those points. Now, our graph is above the asymptote. So our range would be all y values, y element of R. However, it must be the values of y which are greater than q. Take note that I'm not writing as greater or equal to, because our graph will never touch the asymptote. It's not defined the asymptote. However, sometimes the exponential is below the asymptote. Perhaps it can be like that. Now, if this is our asymptote, y is equal to q, it means our range would be y element of R, all real numbers, which are less than q. The last type of function, it's not very common for them to ask you, but it's a straight line. It's rare that they ask you for domain and range, but in case they do, let's suppose we have a straight line like this one, a random straight line. It's easy to see that any vertical line drawn will encounter our straight line. We're drawing it from the x-axis, by the way. So it means our function exists for all values of x. So our domain would be x is all real numbers. Same applies if we draw a horizontal line. It's going to touch our straight line at some point. So here I can say the range is y element of R. This is always the case, except for the two cases where your straight line is parallel to the x-axis. The straight line is y is equal to k. Then here we can see still our domain is all values of x, because we will always encounter our graph. So domain will be x element of R, and range will only be y is equal to k. I'm sure you can figure out for the other scenario. Alright, now we're going to look at a few questions. And our first question is this one here. The sketch below represents the graphs of f of x. As you can see, this is definitely a hyperbola, is equal to g of x, which is definitely a straight line. Y is equal to mx plus c. Point B is 3, 6, lies on the graph, and the two graphs intersect at points A and C. Right, so let me just copy down these quickly. F of x, 2 over x minus 3 minus 1. F of x equal to 2 over x minus 3 minus 1. You also have g of x equal to dx plus e. Let's quickly confirm. Yes. Now we are told that the two graphs intersect at points A and C. That's point there, and that point is a point of intersection. And we know that at the point of intersection, F is equal to G. What does the first question say? Write down the equations of the asymptotes of F. They're giving us 2 free marks for that. Now, we said that our asymptotes can be read off from the function. Remember we said x is equal to p and y is equal to q. So these are the asymptotes that we get reading off from here. If you don't want to be confused by that, you can write it as x minus 3 is equal to 0 and solve for x. That would give you the asymptote. Next question. Write down the domain of F. Now you may scroll back, but remember that domain refers to x values, and we said for a hyperbola, your domain is x element of R, and x is not equal to p. But in this case, we know our value for p. P is the asymptote. So we are saying x is not equal to 3. You can easily see it from there. Our graph will never be equal to 3 since it's an asymptote. Right, next question. Determine the values of d and e correct to the nearest integer if the graph of g makes an angle of 76 degrees with the x-axis. Now coming back to our diagram, we are told that this straight line makes an angle of 76 degrees. What does that remind you of? Takes me to paper 2, where we normally deal with analytical geometry, angle of inclination. Remember we said our angle of inclination is m is equal to tan theta, where this is our theta. We already have, from this formula, our gradient. M is equal to tan 76. If you calculate, you get 4.01. However, they want their answer to the nearest integer. So we're just going to round it off to 4. From this point now, remember an equation of a straight line is y is equal to mx plus c. Even though in this case they gave us dx plus e. So our answer here that we got, which we call m, is in actual fact d. So from here now, we look for an additional point which we can use. And if you analyze your graph, you will see that our straight line passes through the point B is 3, 6. We are going to use that point to calculate the Y-intercept, which happens to be that point there, where the line cuts the Y-axis. And allow me to use this format. My y1 and my x1 are this point B that you see. The 3 is going to be my x1 and the 6 will be my y1. I'm going to substitute now here. y minus 6 is equal to 4 into x minus 3. We'll quickly check. Yes, x1 is 3, y1 is 6. Now simplifying this, we have 4x minus 12, taking the negative 6 over, comes plus 6. We end up with 4x minus 6. This is the equation of g of x. Next question requires us to determine the coordinates of A and C. Let's go back to our graph and identify where A and C are. A and C. There's something special about A and C. Like we said, these are the points of intersection between the two graphs. If you remember from part 1 of this video, we said that at the point of intersection, the two functions are equal. So we're going to equate them. We form an algebraic equation and solve for x. We will probably get two values of x. As you can see, there are 2 points of intersection. So we'll get 2 roots from that. Right, we have 2 over x minus 3 minus 1 is equal to g of x, which is 4x minus 6. Now we need to solve this algebraic equation. This is fun. Alright, so we will obviously start by multiplying each term by the LCD. And when I do that, I'm going to end up with this. And we're going to simplify this. Take note that I'm using brackets. Please use brackets in the right places. If you don't use brackets here, you'll end up with something incorrect. And here we're going to FOIL. And then we collect like terms. Our final equation will be 4x squared minus 17x plus 13 is equal to 0. Let me go back to my favorite color. Right, we're going to factorize this. Another alternative is to use the quadratic formula. But I'm going to factorize. So I'm going to use product, sum, factor. This is one method I use to factorize quadratic equations which are not so straightforward, especially if the coefficient of x squared is not 1. So the product here is the A term times the C term. This gives me 52, saying 4 times 30. The sum is the middle term. This is the sum. Negative 17. Excuse me a second. Negative 17. And then factor refers to two numbers whose product is 52 and whose sum is negative 17. Just quickly going through my mental maths here, I'm getting 4 and 13. 4 multiplied by 13 does give me 52. But now I want them to give me negative 17. So obviously both of them have to be negative. I'm going to rewrite this is 4x squared. Now I'm replacing negative 17x with these two numbers here. Minus 13x minus 4x plus 13 is equal to 0. Take note that these two numbers give me negative 17. So I haven't changed much here. Right, moving on, now I do factorization by grouping, which I learned in grade 9. Factor out x, I have 4x minus 13, and I factor out negative 1 here. I have 4x minus 13, and I end up with x minus 1. Sorry, I forgot equals to 0 here. And into 4x minus 13, which is equal to 0. Now this gives me two values, x is equal to 1 and x is equal to 13 over 4. Let's quickly go back to the question. The question says determine the coordinates of A and C. So we know that coordinates refers to x and y value. Now that we have the x values, remember A and C are at the points of intersection of G and F. We can take our x values and substitute them either in F or in G. But since I like to make my life easy, I'm going to substitute in G. Remember we said G of x is 4x minus 6. And always remember that G refers to y, or F refers to y. So my y value, I'm going to substitute the first x value that I obtained, and I'm getting negative 2. And then this gives me the coordinate 1 and negative 2. Now I'm substituting the second x value which I obtained, which is 4x into 13 over 4 minus 6. Excuse me. 4 into that, we've replaced x with 13 over 4. And a quick calculation will tell us that we will end up with 7. Our second coordinate is therefore 13 over 4 and 7. But we need to make a choice here. We need to decide which one is A, which one is C. Going back to our graph, as you can see from the position of A will obviously be the smaller x value, and C will be the bigger or larger x value. So for our x values, we have 1, we have 13 over 4. 1 is smaller, which makes this A, and at C, we are done. Right, moving on to the next question. For what values of x is g of x greater than or equal to f? Beautiful question. When is g greater than f? So whenever I see this question, I would like to reinterpret it, write it in a language that I can relate to. They're basically asking me, where is g above, or they say greater, where is g above f? And sometimes it helps me to introduce some colors here. There is my f, which is blue. is G, which is green. So if I were to rephrase the question, they're basically asking, where is green above red? So I'm going to go to, sorry, not red, but blue. Green above blue. Where is green above blue? So I'm going to highlight or mark off all the places where green is above blue. Starting here. And here. Up to that point. The places that I've marked indicate the areas where green is above blue. So what I need to do now is to write it down mathematically. I obviously need to know the coordinates of this point, which happens to be A. Remember, I calculated A, and I found that x is equal to 1 here. And at this point, x is equal to 13/4. And then this vertical asymptote, we already agreed that this is y, excuse me, its x is equal to 3. So you can see that green is above blue from this point here, which is at x is equal to 1, right up to the asymptote, which is at x is equal to 3. So we can say from 1 to 3. But now we need to decide whether 1 is included, whether 3 is included. Let's go back and check the question. If you look at the question, they use greater than or equal to, which is not a strict inequality. So here we can say greater than or equal to 1. It would be nice to write less than or equal to 3. However, we cannot do that because the blue graph is undefined there. So we will put a strict inequality, leaving our answer as this. This is not the only place where green is above blue. Like we said, at the point C here, green is above blue. And point C is 13/4. From the looks of things, green is going to be above blue until infinity. So what we can say here is that x greater than or equal to 13/4. The final question asks us to determine an equation for the axis of symmetry of f which has a positive slope. please refer to part 1 of this video, where I give the equations of the axis of symmetry, fastest way to get them. But in case you find it hard to remember, let me see if I can help you. Remember, hyperbola is written as a over x minus p plus q. The equations of the axis of symmetry actually comes from this part here. Just copy that as it is and write y is equal to x minus p plus q. We're going to have two equations of the axis of symmetry. So you're going to do that, plus or minus. One of the equations is a positive slope, the other is a negative slope. In this particular question, they want an equation which has a positive slope, as you can see. Now, how do we go about doing that? Let's make life easy for ourselves. The function that we're given is f of x is equal to, let me just quickly refer, 2 over x minus 3 minus 1. 2 over x minus 3 minus 1. So what you have to do is just circle this part. This is the part that you have to circle. So your equation will be y. Since we want the equation with a positive slope, it will be x minus 3 minus 1, which gives us x minus 4. We are done. If the question instead was the axis of symmetry with a negative gradient, let's say, for instance, they said negative gradient. The question wanted axis of symmetry with a negative gradient. We would have done the same thing. Still, you just circle that part. Then you write it down as y equals to x minus 3 minus 1. However, since you want a negative gradient, you just put that part in brackets and put a negative here. Then you simplify to get negative x plus 3 minus 1, which gives you negative x plus 2. Alright, however, we know the question doesn't ask for negative gradient. The question wants positive gradient. Now there's an alternative method. If you are old-fashioned, like some of the people that I know, you would want to do it the old-fashioned way using y is equal to mx plus c. What you need to remember, however, is that m must always be 1. For an axis of symmetry of a hyperbola, m is either plus or minus 1. So in this case, since we want a positive gradient, we know it's y is equal to x plus c. And then we choose an alternative point, an additional point which we'll get from the point of intersection of the asymptotes. We know that this point is 3 and this is negative 1. So this makes our coordinate here 3, negative 1. So we take that and substitute here. Negative 1 is equal to 3 plus c, meaning c is equal to negative 4. Then you conclude that y is equal to x minus 4, which gives us the same conclusion as we obtained with this initial method. So, choose you this day which method you're going to use. For our next problem, we're going to look at a parabola, and in this question you can see it's infused with a straight line. The sketch below represents the graphs of f and g. G is equal to mx plus c. We are not given m and c. We will probably be asked to calculate that later. D is a point on f. Let's look for D and decide, okay, there is D there. And E is a point on G such that DE is parallel to the y-axis. Please refer to part 1 where I explained what it means for a line to be parallel to the y-axis or perpendicular to the x-axis. A and B are the x-intercepts of f, as you can see evidently. The straight line G passes through point A. H is the turning point of the graph of f. Now the first question asks us to write down the domain of G. So G is our straight line. Now to find the domain, we can reason it like this. If we were to draw a line vertical from the x-axis, are we going to encounter the graph? So if you check any random line that you draw from the x-axis, will always coincide with the graph at any point. Even if we're to extend we will surely coincide with our graph. What it means is our graph exists for all values of x. Therefore, I can say that our domain is x is all real numbers. This is our domain for the straight line graph. You may also want to refer to the beginning of the video. Next question, determine the length of AB. Length of AB. Very nice question, in that you can see that A and B are on the x-axis. The implication of that is that y is equal to 0 at both points. But to find the length, we are not going to bother ourselves with the distance formula, since y values are already 0. The length of AB can be obtained by saying x big minus x small. Now the question is, how do we get those two values? Going back to the statement of the problem, we are given f of x is x squared minus 2x minus 3. This is our f of x. Now, we have already interpreted that at a and b, y is equal to 0. These are basically x-intercepts, or the roots. So we're just going to replace this with 0. Remember, f is y. So y is 0 for x-intercepts. Now we solve this. This should probably be x minus 3, x plus 1. X is equal to 3. X is equal to negative 1. Meaning our length of AB, since we said x big minus x small, it will be 3 minus negative 1, which gives us 4 units. 9.3. Determine the average gradient between A and C. So going back to our graph, there is our point C. to find the average gradient, we will need the coordinates of both A and C. So for 9.3, I'm going to start by writing down my coordinates for A. We already found out here that the x-intercepts are either 3 or -1. So for A, it's definitely -1 and 0. Now we need the coordinates of C. As you can see, that this is on the y-axis. It means that x is equal to 0 here. Just going to write 0 there quickly. Now I need the y value. I do not need to substitute in the equation of the parabola. This value refers to your y-intercept for the parabola. So no need to calculate it. However, if you feel the need, just let x equals to 0. And then substitute. Now, average gradient, I'm going to write it m average, is given by f of x at A minus f of x at C all over xa minus xc. This is just a fancy way of writing the value of y at A minus the value of y at C over xa minus xc, or the usual formula y2 minus y1 over x2 minus xy. Now substituting, we have -1, excuse me, the value of y at A is 0 minus at C over the value of x, and this gives us -3. This is our average gradient. Next question, determine the coordinates of H, the turning point of F. Now for our turning point, we are going to take advantage of the format of our equation, because we can apply a formula to get our turning point. Remember, from part 1, we said x value of the turning point is given by -b over 2a, which is negative. Our value for b is -2 over 2a, where a is 1. This in turn gives us 1. However, for coordinates, we need both x and y. So now we substitute to get y, and just replacing or substituting in the given equation, and I'm getting -4. And then I write my answer as a coordinate. The turning point, which is H, is 1 and -4. Next question. Determine the equation of G if the graph of G is perpendicular to that graph, y minus 2x minus 5. Y minus 2x minus 5 equals to 0. So the main point here is that G is perpendicular to this line. So before we can do any further analysis, we're going to write this in standard form of y is equal to mx plus c, which will give us y is 2x plus 5. So what it means is that m here is equal to 2. Now for two lines which are perpendicular, we know that the gradient of the first line multiplied by the gradient of the second line should give us -1. So our line G is perpendicular to that line that we're given. So I need to calculate the gradient of G. And to do that, we are going to say 2 multiplied by m2 equal to -1. We can divide both sides by 2, and we get m2 is -1/2. This is the gradient of G. So that's our m. Now we need a second point, and let's check. From our graph, we can see that G passes through A, and we already have the coordinates of A. We already calculated them, so we're going to use them to find the Y-intercept. So I'm going to use this format. Y minus y1 is equal to m into x minus x1. Now we have A. We said A is -1 and 0. Minus 0, -1/2, x minus -1. That gives us -1/2x minus 1/2. Means this is our g of x. Moving on. For what values of x is g multiplied by f greater than or equal to 0 if x is greater than 0? What a delicious question that we're dealing with here. This is question 9.6. 9.6. We are saying g of x multiplied by f of x should be greater than or equal to 0, given that x is greater than 0. Let me just quickly confirm g times f. Okay, that's fine. We're interested in the values of x. Values of x. But we have a condition that x must be greater than 0. Now, before we go to our graph, let's analyze what this means. We're saying g times f is greater than or equal to 0. The question we're asking ourselves is, when we are multiplying two numbers, we are going to get an answer that is positive or equal to 0. For that to happen, both numbers must be positive, or both of them must be negative. In essence, what we are saying is, for the first scenario, this one here, we are going to go to our graph and look for places where both are below x-axis. That's what it means for f and g to be negative. They must both be below x-axis. That's where y is negative. And then once we're done, investigate again where they are both above x-axis. So let's look at the first scenario where they are both below the x-axis, if ever there is such a place. Both below the x-axis. If you look at point A, use a different color. From point A, I'm tracing the graph of f. The graph of f is negative throughout here because it's below the x-axis up to that point. Then now I'm looking at g. G is also negative because it is below the x-axis. In fact, g is below the x-axis up to positive infinity, starting from A. Now the question is, where do the two intervals meet? When are they both below the x-axis? My answer would be this area here. This is where they are both below the x-axis. In other words, starting from A and ending at B. And we have the coordinates of both A and B. For A we got -1, and for B, remember here we got 3. This must be B. So I would say from -1 to 3. But are we going to use a strict inequality, or are we going to use or equal to? Are we going to use a strict inequality or not? The answer to that is going to be guided by the question itself. We're not given a strict inequality. So our answer is going to be from -1, that's equal to x, that's equal to 3. That's the first case, where both are below the x-axis. Now we examine if there are instances where both are above the x-axis. Quickly go and check. Now I'm just going to highlight where I think they are both above the x-axis. You tell me if you agree with me. Here, f is above the x-axis. F is positive here. And it so happens that g is also above the x-axis. G is positive here. That is the only place where they are both above the x-axis. If you look at the other place where f is above the x-axis, this is the case. However, g does not appear above the x-axis. In fact, g appears below the x-axis. So we are not interested in this scenario. We only want the case where they are both above, because we want to get a positive answer when we multiply the two. So the second scenario would give us x less than or equal to -1. Those are the two cases. Moving on. The next question says, determine the positive x value for which dE is 7.5 units. Positive x value, dE, 7.5 units. Let's go back to our graph. We have dE. Please notice that dE is perpendicular to the x-axis. This was stated in the problem. So if dE is perpendicular to the x-axis, it means all values of x, the value of x is constant throughout dE. The only value changing is the value of y. In any case, to find the length of dE, we're told that this is 7.5 units. So we're interested in the value of x that makes that possible. If we take dE as a length that we need to calculate, we would obviously say y big minus y small. Y big minus LDE is equal to y big. We're doing this only because the value of x is constant. The problem is we do not have either of these values. However, we know that y represents the function f and y small represents the function g. Let me just show you for a moment. This is our y big, which is at d, and y small, which is at e. Now if you notice, d is on f, while e is on g. So to find the length of dE, we basically need to subtract the two graphs. F minus g. So in other words, we are saying f minus g is equal to 7.5. Now, f is x squared minus 2x minus 3 minus. Now we want g. What was g? G is negative half x minus half. Negative half x minus half. Let me emphasize that we're subtracting a binomial, a trinomial. Please use brackets. Now this difference should give us 7.5. Let's start by getting rid of 2 and the bracket. So we're going to multiply everything by 2. And we get 2x squared minus 4x minus 6 plus x plus y equals to 15. I'm going to try and write this in standard form. 2x squared minus 3x minus 20 equals to 0. I'm going to factorize this my old-fashioned way. It always works for me. Product, sum, factor. I usually use this method if the coefficient of x squared is not 1. Now remember, my product is a times c, so I'm having negative 40. My sum is negative 3. So I'm looking for two numbers whose product is negative 40 and whose sum is negative 3. I can think of 8 and 5. for me to get negative 3, I'm going to give the bigger number the sign of 3, negative. Now if I multiply these two, I get negative 40. If I add them, I get negative 3. So I'm just rewriting my equation now as 2x squared minus 8x plus 5x minus 20 equals to 0. Take note that this is the negative 8 and this is the 5. From here, I'm going to do factorization by grouping, which I learned in grade 9. This is x minus 4 plus 5, x minus 4, 0, x minus 4, 2x plus 5 equals to 0. Solving further, I get x equals to 4, x equals to minus 5 over 2. Now let's recap on the question. Determine the positive value of x for which d is 7.5. So we obtain two values of x. Now the question requires the positive value. So we are going to conclude and say therefore x is 4. The final question. Use the graph to determine for which values of k will f of x equals to k have non-real roots. What a nice question. Just one more time, let's go through it. Use the graph to determine for which values of k will f of x equals to k have non-real roots. Right. 9.8. Go back to the color. We are given f of x is equal to k. And we want non-real roots. We want to obtain non-real roots. Non-real roots. Once more, I'm going to remind you that f is the same as y. So we basically having y is equal to k. I'm saying this because I'm sure we remember how to draw the line y is equal to k, where k is any real number. The line y is equal to k can be at so many different points depending on the value of k. For different values of k, just that we don't know what k is, but all these lines are potential y is equal to k, etc. So the point I'm trying to make here is that the line y is equal to k is a horizontal line which is parallel to the x-axis. And it's going to cut the y-axis at any point depending on the value of k. Now the next thing that I want us to interpret is, what does it mean to have non-real roots? If we go back to nature of roots, non-real roots will be obtained when delta is less than 0. But we're not going to use this. The instruction is clear. Use the graph. So, what are roots? Roots are solutions to an equation. When you solve an equation, what you obtain are roots. Now, for us to get non-real roots, as an example, in the first video, I said that for us to get non-real roots for a parabola, it means your parabola does not intersect the x-axis. What it means is if you are to try and solve the quadratic equation for this parabola, you will get no solutions. This is because your parabola does not intersect the x-axis. Now, coming back to our problem, if you're saying f of x is equal to k has non-real roots, we are saying that the function f and the line y is equal to k have no point of intersection. That's what it means to say non-real roots. It means they do not meet anywhere. If we were to try and solve the equation f of x is equal to k, we would get no solutions because there are no points of intersection, as in this example. Let's go back to our function. Now remember, I said y is equal to k is a horizontal line. It can be drawn anywhere. But now we have a restriction. Our horizontal line must not intersect with our parabola. They must not touch each other. For that to happen, it means our line y is equal to k cannot be above this line here. Just hold on a second. Yes, here. You see, at that point, the line y is equal to k is touching our parabola. So there is a point of intersection. And if I go higher, for instance, if I go higher, see, now I'm having 2 points of intersection. It means I have two roots, and so on. If I want to avoid getting roots, it means I have to stay away from the point H. And the point H happens to be our turning point. It means whatever value of k I choose must be lower or less than the turning point. So at this point I don't have any intersection with my parabola. So I have non-real roots. But as soon as I touch my parabola, I now have real roots. And at this point I have equal roots. So, as you can see, this is a 1-mark question. However, the analysis is quite intense. That's only the first time. But for similar questions, you apply the same kind of logic. Now, if you remember, our turning point, let me just check one more time if we still have it. Yes. We have our turning point here. Our turning point. That's our turning point. I'm only interested in the y value, yTp. So the answer to this question would be k. Excuse me. K is less than -4. This will ensure that there is no point of intersection.